Hello guys, welcome to my channel Algorithm Avenue. In this video, we'll be seeing two basic topics, that is different types of learning, and the second is what is a perceptron. We'll see the perceptron in detail. Okay, first let's continue with the first topic, that is different types of learning. In this topic we have two subtopics, that is one is supervised learning, another is unsupervised learning. In supervised learning, we'll be working on label data. Means let's take an example like dog or cat classification dataset. In that dataset you see that under each image means each image has a boundary, means that image is classified to dog, means that image is specified as a dog, and the next image will have another boundary, that image is specified as a cat. Means in supervised learning you work on label data. Remember that in supervised learning you work on label data. Now let's see unsupervised learning. In unsupervised learning you work on unlabeled data, means there are no labels for the data. Let's say you have similar data set but with no labels. Means in that kind of scenario what happens is when you plot that data set as an data points, you see that similar data is plotted in one region, and another similar data is plotted in another region. Means you have two regions here. Means one region belongs to one class, another region belongs to another class, but you don't have labels in this unsupervised learning, but it's able to understand the similarities in that data set, and it is able to find the similarities and plot the data, and means it is occupying some region, means that class is occupying some region and other class is occupying another region. Means by this you understand that all the data points in this region are similar, means they fall into one class, and all the data points in this region belong to another class, means all the data points in this region are similar. Means any new data point comes into it either falls into this region or falls into that region. By this you can understand that this is one class and this is another class. But in case of supervised learning you have labels. Means already this each data point has dog, or this has cat. Means each data point will have either a dog label or a cat label, but in unsupervised learning you don't have this labels. This is the basic definition of supervised and unsupervised learning. So, okay, now in the next section we'll be covering what is a perceptron. Okay, now let's see the discussion on perceptron. Means in brains we have generally neurons, right? We have brain neurons. What that brain neuron does, it means what is seen by our eyes, it goes through the brain neurons, and some calculations, some reactions are done, and your brain understands what you have seen. In the similar way, in basic neural network we have perceptron. Means initially in late 1950s we used to have a neuron called perceptron. A perceptron is an artificial neuron. Means similarly how brain has a biological neuron, and neural network has an artificial neuron called perceptron. A perceptron is a fundamental block of a neural network. Means in a very deep neural network where you have millions of perceptrons, or millions of connections, the basic one perceptron is called a fundamental unit of a neural network. So now let's see what is the task done by the perceptron. The perceptron is generally used to do supervised machine learning task. We have just seen what is a supervised learning, right? Means in supervised learning you classify label data. This label data is used to classify with the help of perceptron. This is the function of the perceptron. Now let's see the basic structure of a perceptron. Okay, structure of perceptron. Okay, initially we'll have some weighted some calculator. This is our bias multiplied with some quotient. These are our features, let's say x1 and x2. Corresponding to this we'll have weights. We'll see further what are these weights, what is this bias, and here z is calculated. We'll also see how z is calculated in this process and pass through activation function to calculate y hat. Means y hat is a predicted output of this perceptron. Okay, now let's see each in detail. First, let's see what are the layers present here. Layers. Okay, we have two layers in perceptron. One is input layer and other is output layer. Generally, in neural networks, we'll have three layers. One is input layer, hidden layer, and output layer. But in an perceptron, in a single layered perceptron, we will have two layers. One is input layer, and next is output layer. So these are the two layers of a perceptron. Okay. Now what does this input layer does? Let's see. These are our inputs. Means input layer is used to help the inputs pass through this weighted sum calculator. Means these inputs are passed through this weighted sum calculator, and z value is calculated here. And for this z value, bias b is added. Okay, let's see how it is done. Now z is equal to w1 x1 plus w2 x2 plus b. These are your inputs of the data and these are your weights. Means for each input we'll have an specified weights, but for a single perceptron we'll have an corresponding bias. Means if you have 10 perceptrons in an layer, you'll have 10 biases, but means for each perceptron will have a single bias. Okay, we'll see further what are these bias and weights. Let's see how basically how it is calculated. Means when these inputs are passed through this weighted sum calculator with multiplied with w1 and w2 and added with bias, you will get the output as z. Okay, in this way z is calculated. Okay, now let's see what is an activation function. Initially when perceptron was developed, we used to have step function. What is a step function is, in step function, if the values, if means if the z value is negative, then the values are 0. Means y hat value is 0. If the z values are positive, then the y hat values are 1. Means the step function does only two things, either 0 or 1. When the z value is positive and it is passed through activation function, you will get 1, and then when this z value is negative and passed through activation function, you will get 0 for that corresponding input. Okay, now let's see another activation function, that is sigmoid activation function. We'll see this activation functions in detail in further videos, but basically to understand this perceptron, we only need two activation functions. One is step function and other is sigmoid activation function. The sigmoid activation function, the graph is yeah, this is the threshold value 0.5, this is 1, this is 0. Means when the z value, when the z calculated means when the after calculating the z value passing through the activation function, if the values are above 0.5, the y hat value is 1, and if the activation function output is less than 0.5, then the y hat value is 0. But the step function is an discontinuous function, the sigmoid function is an continuous function. In step function you either have 1 or 0 values, but in sigmoid activation function you will have values ranging from 0 to 1. Means 0 your activation function can be, output can be 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.435 or 0 0.6, 0 0.7, anything. But the values above 0.5 are 1 and the values below 0.5 are 0. Okay, this is the function of activation functions. It helps the z value is generally greater. You'll have some big larger values for the means you see that all the values here calculated are like multiplication, addition, so you'll get some greater values. So these greater values should be scaled. So this scaling is done by the activation function. Okay, this is the basic function of activation function. So after passing through activation function, f of z is equal to y hat. After calculating this y hat is generally called predicted output. Predicted output. Let's say the corresponding you have a data set where x1 and x2 are your input features, means that is your input data, and y is your corresponding output to that x1 and x2 values. Let's say y is your actual output. Actual output for this x1 and x2 input data, this is your actual output. And for this x1 and x2 data, the model has predicted an output called y hat. Now what after calculating this y hat, what happens is the model calculates the error is also called as loss, but initially for basic understanding I am calling it as error. Error is calculated by actual output minus predicted output. Initially, you will get this error value greater, but after a few steps of training, the error value is generally reduced. Okay, after calculating this error, the error will be generally larger value. Okay, so after calculating this error, you will see that some larger you'll see a difference between the your actual output and predicted output. Now your aim is to reduce this difference. So how can you reduce this difference? These two are fixed values. Okay, these two cannot be altered. So what you can change to minimize this error? You can change bias and these two weights, right? These parameters can be changed to calculate new y hat value and the error can be reduced. So now what happens is you do weight updation and bias updation. Okay, now let's see weight updation and bias updation. Okay, now what you have done is you calculated the error. After calculating the error, you see that it is some larger value. Now your aim is to reduce the error. So to reduce the error, we have only one option to alter this weights and biases value. So how can we do this? By this can be done by a formula called Wi is equal to Wi plus learning rate into error into xi, and bias updation can be done by b is equal to b plus learning rate into error. Okay, now let's understand these formulas. First, wi is your old weight value, means initially what you have given, that is the wi value. Next is learning rate. This I'll explain you this learning rate with an example. Let's say someone has given you some book to complete it. So what you can do is you can complete either in 1 day or you can take 100 days to complete that book. So when you complete it in 1 day, you do faster learning, means you'll have some contextual idea, but you will not have some depth idea about the topics. But when you complete in 100 days, you will have conceptual idea plus in-depth knowledge about the book. So learning rate is nothing but when your values of learning rate are higher, the weight updation is done greaterly, means old weight and new weight value will have wi old minus wi new will be greater value, means old weight and new weight will have a larger difference when your learning rate is greater. But when your learning rate is smaller, this difference will be less. You can see some, you can either put some values and see how these weights are varying. So this is your learning rate, Means initially the learning rate always should be initially, and after some training, the learning rate must be a lower value, always a lower value. The learning rate must be always fixed to a lower value. Remember that learning rate must be always fixed to lower value. So this is learning rate, and this is your error calculated. This is your xi, means the input. So these are your weights. Means we are, let's say we are calculating w1. W1 is equal to, means w1 new. Let's say this is the new weight, this is your old weight. Let's say w1 new is equal to w1 old plus learning rate into error into x1. Means corresponding to this x1 value, what the weight is there, that will get updated. Let's take this as w2. W2 old is w2 new is equal to w2 old plus learning rate into error into x2. Means this w2 weight will be updated. Means when the next input is given, the new weights are multiplied to the input data and new bias is added. Okay, in this way, until your error is reduced, and means until you get minimal error, your updation and back propagation will be continuing in the similar way. Means first you assign some random values to this weights and bias. Similar way this bias is calculated, I have not explained you, but similar way this bias is calculated. Means initially what you do is you assign some random values to this bias and this weights, and your input data gets multiplied. Let's say you have first row of your data that is getting multiplied with x1 and x2 multiplied with w1 and w2, and some bias is added and weighted sum is calculated. You pass through activation function, you got some predicted output, and you have calculated the error between that actual output and the predicted output. And after calculating this error, you see that the error value is larger. After this, that larger value, what to reduce that larger value to some smaller extent, what you do is you go back and you calculate the new weights based on that error and learning rate. You update the weights, and next time when the new input, means second row of data is passed, that new weights, means new parameters, will be multiplied and added, and in the similar way forward propagation is done. Means for each input, this process goes on until your error is reduced. Okay, this is the structure of an structure and functioning of an basic neuron. Okay, now let's see two things. One is training time and second is testing time. What happens in training time? What happens in testing time? We'll see these two things. In training time, we have seen previously with how the inputs are forwardly propagated, and weight updation is done by calculating the error. That all is done in training time. In training time, the weight updation and bias updation is done. Weight and bias updation. These two things are done in training time. But in case of testing time, these two things are not done. Means weight updation, bias updation is not done in case of testing time. Already in training time, what happens is, in your total training time, your main goal is to calculate the fixed values of this weights and bias. In your training time, your aim is to calculate the fixed values of this weights and bias. This is your initial aim of your training time. So after completion of your training, you'll get some fixed values of your weights and bias w1, w2 and bias b. So after total training time, you'll get these fixed values. So now comes the testing time. In case of testing or prediction, or let's say prediction time. So in case of testing and prediction time, these fixed values of weights and biases are multiplied and added with your test data or prediction data, and y hat is calculated. But in case of train time, what happens is the weights and bias values will be varied time to time. But after at the end of the training, you'll get some fixed values of weights and bias. But in case of testing value, you only work on fixed values of weights and bias. You don't again calculate this weights and bias again. So this is training time and this is testing time. Now let's see importance of weights. I'll be explaining you the importance of bias at the end. Now let's see importance of weights. Importance of weights in perceptron. In perceptron or in any kind of neural network, the importance of weights will be similar. What the weights does is, means you have some input data. Let's say x1 is your input data, x2 is your input data. The corresponding weights are after at the end of your training, the corresponding weights are calculated to be 0.9, 0.1. These are your corresponding weights for your corresponding inputs. Okay. Now this 0.9 value is greater than this 0.1. Means in calculating the y hat value, this feature plays a major role. Then this feature means in calculation of your y hat value, means in calculation of your predicted output, this feature is playing a crucial role. Then this feature means the importance of weights tell you that when you see the final weights value after this training, you will observe that this value means this value is greater than this value, means this feature is more important than this feature. So this is the basic function of your weights. It helps in determining the which values are important, means which features are important in calculating the output in an basic perceptron or a neural network. Okay, now let's understand the total entire discussion with an example. Okay, this is your data. Let's say these are your this is your quality of bricks. This is one feature, and this is the quality of cement. This is another feature. This is your y actual output. Let's say this is x1, this is x2, and this is your y. I hope it's visible, right? Okay, this is x1 value initial and means first row. First row. This is x1 value. This is x2 value. This is your actual y output. Okay. Now let's do the mathematical intuition. 78 means you know that when you pass this data to an perceptron, you will get the equations like x1 w1 plus x2 w2 plus b is equal to some z value. Yes, right? After you will get I have shown you this equation, right? Similarly, if you substitute these values in this equation, 78 into, let's say w1 and w2 are, w1 is equal to 1 and w2 is equal to 2. Okay, let's assume these are your weights. Let's say 78 into 1 plus 90 into 2 plus bias b, let's say bias b is equal to 1, is equal to 78 into 1, 180, 180, 160, 269. Okay, this is the 269 value. This is the calculated z value. Now after calculating the z value, what have you done in Perceptron? This z value is passed through an activation function, right? Let's assume that activation function used here is a step function. What is the function of step function? When the output is positive, it scales it as 1, and when the output is negative, it scales it as 0. Okay, the output you got here is positive, means the y hat value after f of 269 is equal to 1, means after passing this positive value to an activation function, you got an output as 1. Let's say suppose you take a negative weights here, you will get a negative output, right? The output is 0, but in the actually this is your actual output, right? This is your actual output, y is equal to 1. This is your predicted output y hat. Let's say you taken some negative value to the weights and you got your output as 0. Activation function output as 0, means you see that there is a difference between y and y hat. Okay, now what happens? You calculate error. Error is equal to 1 minus 0 is equal to 1. Now after calculating this error, what you do is you calculate your new weights and bias value based on this error. Okay, I have shown you that formula, right? Similarly, substitute all the elements in that formula and calculate new weights and your new biases. Okay, after calculating the new weights and bias, you will get w new, w1 new, w2 new, by new bias. Okay, these new weights and bias are multiplied and added to this second set of inputs. And similarly, if you have a third set of inputs, similarly the data gets added and multiplied. So how many inputs you have, that many times your weights get updated and your error is minimized. So this is the basic intuition of your perceptron with an example. Okay, now let's see what are the basic similarities and differences between an biological neuron and an artificial neuron, that is perceptron. Okay, now let's understand what is how an biological neuron looks like. These are the dendrites. These dendrites help in taking the input. Means when your eyes see something, the input from your eyes passes through your eyes and from the eyes to the neuron. In this neuron, this dendrites helps in taking the input. After passing this input to the nucleus, some biological reactions takes place in this nucleus and an output is generated. This generated output passes through this axon. From the axon, it passes through the synapses. From synapses, this synapses gets connected to the other biological neurons. So from this synapses, the output is passed through the next neuron. In this similar way, some millions of connections are there in a human brain. So input from one neuron passes through some millions of neurons. So this is the basic biological structure of a neuron. Now let's see in perceptron. In perceptron, this is your input. Means similar to these dendrites, these are your input connections. So from these input connections lead to some weighted sum calculator. Means similar to nucleus, how the dendrites pass the information from this input layer to the nucleus. From here the input data is passed through the weighted sum calculator. From the weighted sum calculator it goes to the activation function and output comes out. Similarly, in the biological neuron, from the dendrites it goes to the nucleus, some output is calculated and the output is passed through this axon and from synapses and next neurons. So these are the basic similarities between a biological neuron and perceptron. Now let's see the differences between these both. Okay, we have very few basic differences. Okay, what is the first difference is these dendrites takes millions of inputs, but in case of a perceptron it only has limited number of inputs. Means if you give some n number of inputs to this perceptron, it cannot perform really well. But in case of dendrites, only this one single neuron takes the input, some millions of inputs, and performs really well. Okay, now next difference is uh, okay, now let's see the second difference. The second difference is we cannot understand what's happening inside this nucleus. Okay, in this nucleus even scientists don't know what's happening inside this basic small nucleus. Okay, in this nucleus some complex operations takes place, but in case of a perceptron, you'll see that basic mathematical operations are taking place. Means just calculating the weighted sum and passing through an activation function. Means some basic operations takes place here, some complex operations are done here. Okay, these are the two differences between the neuron and a perceptron. First difference is millions of inputs, limited number of inputs. Second is you can't determine what's happening inside a nucleus, but here you can determine what's happening in perceptron. Okay, these are the basic differences and similarities between a neuron and a perceptron. A perceptron is structurally inspired from the neuron, but the operations are not inspired. Means structurally it's same, but the operations are different. Okay, okay, let's see the geometrical intuition of a perceptron. Okay, this is the basic structure of a perceptron. And these are let's say from the previous example we plotted some data points based on the bricks, quality of bricks and quality of cement. These are the data points that we plotted here. Okay, now let's start from here. Okay, let's see how z is calculated. Now z is calculated by z is equal to x1 w1 plus x2 w2 plus bias b. Okay, now let's say x1 is equal to capital X, X2 is equal to capital Y, W1 is equal to A, W2 is equal to B, and B is equal to C. Means weights are A and B, bias is C, X1 and X2 inputs are X and Y. That is, one is quality of bricks, one is quality of cement. Okay. Now let's rewrite the equation. Z is equal to AX plus BY plus C. You see that this is a basic line equation, right? This is a basic line equation. Means what perceptron does is it draws a line separating two regions. Means let's say you have bricks on the x-axis and cement on the y-axis, right? When you plot these data points, you'll get stronger houses one side and the weaker houses on the other side, right? Similar kind of data is generally in a basic graph also. Similar kind of data is plotted at the one region, and another similar data is plotted in another region. Similarly, and data is plotted in two regions. This is one weaker houses region. This is a stronger houses region. Okay. Now what a perceptron does is it draws a line separating two different regions. Means these two different regions are your two different classes. Let's say this is your weaker houses and this is your stronger houses. Means you see that a perceptron is drawing a line separating a two different regions, classifying data to one or another. Okay, this is the basic function of an perceptron. Okay, now let's see for how it looks for a three-dimensional data. Means you have three inputs, let's say x, y, and z are your inputs. Okay, now let's write for a three-dimensional data. Z is equal to ax plus by plus cz plus b. For this, for three-dimensional data, what a perceptron does is it creates a plane. Let's say this is the plane. These are your data points. You have similar kind of data here, similar kind of data here. What a perceptron does is it draws a plane separating these two regions. Okay, when you have more than three-dimensional data, how the region is created is hyperplane. Hyperplane is created to separate for a four-dimensional or more than that. Okay, okay, you observe that the line is created here, right? Means above this line are one class, below this line are another class. Means you can write your data as for one class, means that is when z is equal to, when the new calculated z value is greater than or equal to this ax plus by plus c line. Means when your new calculated z value falls under this region, it is classified into stronger houses. Means this is one class. Another is when your z value is less than this line, by plus c. Means when your z value, when your calculated z value is below this line, it falls into another class. Means weaker houses class. Okay, in this way a line is drawn to separate a line or plane, or a hyperplane is drawn to classify two different classes by the perceptron. This is the basic definition of a perceptron. A perceptron is a fundamental unit of a neural network, or is an artificial neuron which is helpful to classify a binary data, which is used to which is used as a binary classifier in classifying a data, linear data, in classifying a linear data into one or another. Okay, let's say the definition again. A perceptron is an fundamental unit of a neural network, or is an artificial neuron which is a binary classifier which classifies the linear data into one class or another class. Okay, this is the basic definition of a perceptron. In this way, perceptron classifies a linear data into one class or another, and this is the whole geometrical intuition of a perceptron. Okay, now we have another topic, that is bias, importance We have seen the importance of the weights, but we have until now we have not seen the importance of the bias. Suppose you don't have bias in your data, means this b value is 0. Let's say this b value is 0. Means if bias is 0, means you don't have a bias term. Okay, this bias value is 0 means the line is passed through the origin. Okay, the line is passed through the origin. When your line is passed through the origin, for this data it's unable to classify into two different classes, right? Yes, right. When your bias value is 0, it passes through the origin. Your data points are in this way. Means this the means according to this perceptron, what you have seen is this region falls into one class and this region falls into another class. But here you see that your data points are in this way and it's classifying totally wrong. So you understand the importance of your bias, right? When your bias term is not 0 and is some random value, what happens is it has an ability to draw a line. Means this line is drawn according to your data. Okay, it creates an ability to the perceptron to draw a line separating the data perfectly. When your bias term is 0, it passes through the origin and you will not have an uh, you will not have a very good geometrical boundary between the two different classes. But when your bias term is non-zero, you will have a perfect geometrical boundary in classifying the two different classes. Okay. Now we have seen what are the advantages of perceptron. A perceptron is always an binary classifier. Binary classifier. Okay, remember this term. A perceptron is a binary classifier. It classifies only a data into two different classes. Okay, now let's see the different drawbacks of a perceptron. Drawbacks. Okay, now let's see the drawbacks of a perceptron. Let's say this is your graph and these are your data points. These are your data points. Okay. Uh, okay, these are your data points. Means this is your one data and this is your one class and this is your another class. Okay, means this falls under one class and this falls under another class. Means we have seen that a perceptron works well on a linear data. Means the data you are providing to a perceptron must be linear. Means it can be classified by a line or a plane. But in case of non-linear data, means the two different classes are classified by non-linear. Means you know that non-linear lines means this parabola or circle. Means these are your non-linear lines. Means non-linear curves. Okay, when the data is non-linear, your perceptron badly fails. Means it cannot draw a circle to separate these data points and these data points. Okay, this is the biggest drawback of your perceptron. No matter what activation function you use, the perceptron badly fails in classifying non-linear data. The perceptron is always used to classify linear data. Okay, remember this one thing. This is the biggest drawback of the perceptron. It always fails in classifying a non-linear data. Means you will have a bad accuracies. But in classifying linear data or a linear kind of data, perceptron performs well. I will not say really well, but performs well. Okay, this is the total concept on perceptron, and we have covered two topics. One is different types of learning and total intuition on perceptron. Okay, this is the whole video on the different types of learning and perceptron. Okay, this is our end of our discussion. If you like the video, please like, share, and subscribe.